Hello everyone. So now we are going to get into the juicy part of this section, which is implementing a network to classify digits. We are going to code in Python, and I'm just going to follow along this code. You can obviously get the code for yourself. You can use git clone, or you can also download the zip file from here. So let us delve right into it. So alright, let's write a program that learns how to recognize handwritten digits using stochastic gradient descent and the MNIST training data. We'll do this with a short Python 2.7 program. So if you're familiar with Python, you will know that this is far from the latest. Python 2 is no longer like even the standard one. Python 3 is currently the main one, and even in Python 3 you already have Python 3.10 at the time of recording this video. So this script will be outdated, but it will work. It isn't going to not work. You're not going to face an issue like it just won't work. You might have the issue that some dependencies or old versions might take up some time to set up and all. The first thing we need to do is get to the MNIST dataset. If you're a Git user, then you can obtain the data by cloning the code repository for this book. If you don't use Git, then you can download here. Incidentally, when I described the MNIST data earlier, I said it was split into 60,000 training images and 10,000 test images. That is the official MNIST description. Actually, we are going to split the data a little differently. We'll leave the test image as is, but split the 60,000 training set into two parts: a set of 50,000 images, which we'll use to train our neural network, and a separate 10,000 image validation set. We won't use the validation data in this chapter, but later in the book, we'll find it useful in figuring out how to set certain hyperparameters of the neural network, things like the learning rate and so on, which are not directly selected by a learning algorithm. Although the validation data isn't part of the original MNIST specification, many people use the MNIST in this fashion, and the use of validation data is common in neural networks. When I refer to the MNIST training data from now on, I will be referring to the 50,000 image dataset, not the original 60,000 image dataset. So I hope that makes sense. It is quite obvious what he's trying to convey. So as noted earlier, the MNIST dataset is based on two datasets collected by NIST, the United States National Institute of Standards and Technology. To construct MNIST, the NIST data was sets was stripped down and put into more convenient format by Jan LeCun, Oriana Cortez, and Christopher J.C. Burgess. Okay, the dataset is the enough in my repository is in a form that makes it easy to load and manipulate the MNIST data in Python. I obtained a particular form of data from the LISA Machine Learning Laboratory at the University of Montreal. Okay, so you can check these places out. This is the original MNIST website which we had a look at in the previous video as well, and the other one is loading up. So let's see. So apart from MNIST data, we also need a Python library called NumPy for doing fast linear algebra. If you don't already have NumPy installed, you can get it here. Okay, so this is the standard stuff. Like, okay, this website isn't opening up. Let me explain the core features of the neural networks code before giving a full listing below. The centerpiece is a network class which we use to represent a neural network. Here is the code which we use to initialize a network object. So if you're familiar, I'm not going to go into like the nitty-gritties of Python, but if you're familiar with Python, you'll already know what classes and objects are. So, or if you're not, then a good refresher could be great. So you have a class network, and you have the constructor here, and it takes in the parameter sizes. So self.sizes is sizes, self.biases are randomly generated, and self.weights are also randomly generated. So np.random.rand n pick up random weights from the Gaussian distribution, and the number of layers is the length of sizes. Okay. In this code, the list sizes contains the number of neurons in the respective layers. So for example, if you want to create a network object with two neurons in the first layer, three neurons in the second, and one neuron in the final layer, you will use this code. So I hope this makes sense. The biases and weights in the numpy in the network object are all initialized randomly using numpy.np.random.randn function to generate Gaussian distributions with mean 0 and standard deviation 1. This random initialization gives us stochastic gradient descent algorithm a place to start from. In later chapters, we'll find better ways of initializing the weights and biases, but this will do for now. Note that the network initialization code assumes that the first layer of neurons is an input layer and omits to set any biases for those neurons, since biases are only used in computing the output from later layers. So you can see that all the biases are set from the first layer onwards. So we're done with this. Note that also that the biases and weights are stored as list of numpy matrices. So for example, net.weights1 is a numpy matrix storing the weight connecting the second and third layer of neurons. It is not the first and second since Python's indexing starts at 0. So 0 would be the first and second, 1 would be the second and third, and so on. Since net.weights1 is rather verbose, let's just denote the matrix W. Let's just denote that matrix W. It's a matrix such that Wjk is the weight for the connection between kth neuron in the second layer and jth neuron in the third layer. So this is also quite clear. This Wjk is the matrix which forms the connection between the kth neuron in the second and jth in the third. This ordering of j and k indices may seem strange. Surely it would make more sense to show up the j and k around, right? So you might think that shouldn't the k come first because the second layer comes first. But the big advantage of using this ordering is that it means that the activations of vectors in the third layer is this. So if you have, since now you're using this jk notation, you can straight away use this instead of doing some other wavy stuff with w. So using the j first gives you the capability to use the w directly instead of doing some other mathematical operations on w to make it compatible in this equation, which would again make the complexity of this equation a bit more. So there's a bit going on in the equation, so let's unpack it piece by piece. A is the vector of activations. A is a vector of activation of the second layer of neuron. To obtain A dash, which is the uh, activation in the third layer, we multiply A by the weight matrix W and add the B vector B of biases. We then apply sigmoid element wise to every entry uh, in the vector wa plus b, and this is called vectorizing the function sigmoid. It's easy to verify the equation given gives the same result as our earlier rule equation 4 for computing the output of a sigmoid neuron. So I guess this is sufficiently obvious. What they're trying to convey is a dash is the activations in the third layer, a are the activations in the second layer, and they are related by this equation. So before applying the sigmoid, you do the classic linear algebra stuff where you take the weight matrices and the activations and multiply them and add the biases and then apply the sigmoid on each operation. This process of applying the sigmoid element wise to each element of the vector, this is known as vectorizing the function. Okay. So exercises. Write down the equation 22 in component form and verify it gives the same result as the equation for computing the output of a sigmoid neuron. Okay, so let's have a look at equation 4. This is equation 4 and equation 22. This is equation 22. So if you write out uh, this out in component forms, then your W would be a vector uh, which between the kth and the jth, right? And a would again be a vector. So when you multiply them, you'll get the weighted the activations in A multiplied by their respective weights. And then when you add the bias B, then you'll get the activations of A multiplied by the weights and the bias added to them. And then you just apply the sigmoid. So I think this is what they want to ask us, but I'm not really sure what they are trying to ask, what they want with this question. If you feel like I'm not get, if you feel like you have a better explanation for this, then surely do comment it down below. With all this in mind, it's easy to write code computing the output from a network instance. We begin by defining the sigmoid function. Okay, so you have the sigmoid function, and this is just 1 upon 1 plus e to the minus z, which is essentially this. Oh, I accidentally went all the way back. Okay, so I was here. So note that when the input z is a vector or numpy array, numpy automatically applies the function sigmoid element-wise, that is in vectorized form. So that also makes sense. We then add a feed forward method to the network class, which given an input A for the network returns the corresponding output. All the method does is apply equation 22 for each layer. Equation 22 is this equation, and so for each layer it does this. So for B comma W in the biases and weights. So when you do the zip function, you can iterate over both of them simultaneously. All are doing is applying the sigmoid on the dot product of W and A and then adding B. And all this has done has is that it has computed A once again, which are the activations in the next layer using the activations in the previous layer. Of course, the main thing we want our network to do is to learn. So that end we'll give them so that uh, to that end, okay, sorry, I was reading it wrong. To that end, we will give them an SGD method which implements stochastic gradient descent. Here is the code. It is a little mysterious in a few places, but I'll break it down after the listing. So let's have a look at the code. The parameters are self training data, the number of epochs, mini batch size, ETA, and test data. So train the neural network using mini batch stochastic gradient descent. The training data is a list of tuples xy representing the training inputs and the desired outputs. The other non-optional parameters are self-explanatory. If test data is provided, the network will be evaluated against the test data after each epoch and partial progress printed out. This is useful for tracking progress but slows things down substantially. Okay, so first of all, this exchange stuff you won't see much in Python 3. So just a heads up if you haven't seen this before. So let's just look at the breakdown uh, uh, of what they've tried to explain. The training data is a list of tuples xy representing the training inputs and corresponding desired outputs. The variables epochs and mini batch size are what you would expect. The number of epochs to train for and the size of mini batches to use when sampling. Epochs are essentially the number of times you're going to train the model again and again. ETA is the learning rate eta. Okay. If the optional argument test data is supplied in the program, will evaluate the network after each epoch of training and print out partial progress. This is useful for tracking progress but slows down stuff substantially. So this equals to none is done because if nothing is provided, then it would automatically be set to none. So you would have no test data. And since you can see this is in a test loop, so if there is none here and nothing is provided, then you will not enter this loop. So the code works as follows. In each epoch, it starts by randomly shuffling the training data and then partitions it into mini batches of the appropriate size. So you have for in the range of epochs, you randomly shuffle the training data and then make mini batches of of the data randomly. This is quite clear. Then this is an easy way of sampling randomly from the training data. Then for each mini batch we apply a single step of gradient descent. This is done by the code self.update mini batch, which updates the network weights and biases according to the single iteration of gradient descent using just the training data in mini batch. Here is the code for the update mini batch method. So for each mini batch, we will update the our model and using the update mini batch function which they have defined below. So this is the update mini batch function. So up, update the network's weights and biases by applying gradient descent using back propagation to a single mini batch. The mini batch is a list of tuples xy and ETA is the learning rate. So nabla B and nabla W, these are essentially those fancy upside down triangles. They are known as nabla. So they are uh, zero matrices which are initialized using the same shapes. And now for x and y in mini batch, because x and mini batch has two things, the the testing stuff and the actual output which you want, you will use the self.backprop method. Then you will update the nablas and then you will update the weights using the stuff that you got. So most of the work here is done by this particular line. and this invokes something called a back propagation algorithm, which is a fast way of computing the gradient of the cost function. So update mini batch works simply by computing these gradients for every training example in the mini batch and then updating self dot weights and self dot biases appropriately. I am not going to show the code for self.backprop right now. We'll study how backpropagation works in the next chapter, including the code for self.backprop. But now, for now, just assume that it behaves as claimed, returning the appropriate gradient for the cost associated to the training example X. So this is a fair leap of faith which we can make. The author is not obviously not trying to scam us or something. So you make these nablas, then you use them for you get store the back propagation data in them, and then you update them, and then you establish the new weights and new biases using these updated things. Okay, so let us now look at the full program, including the documentation strings, which I omitted above. Apart from self.backprop, the program is self-explanatory. All the heavy lifting is done in self.sgd and self.update minibatch, which we have already discussed. The self.backprop method makes use of a few extra functions to help in computing the gradient, namely sigmoid prime, which computes the derivative of the sigmoid function, and self.cost derivative, which I won't describe here. You can see the gist of these and perhaps the details just by looking at the code and the documentation strings. We'll look at them in detail in the next chapter. Note that while the program appears lengthy, much of the code is documentation strings, intended to make the code easy to understand. In fact, the program contains just 74 lines of code, non-whitespace, non-comment code. All the code may be found on GitHub here. Okay. So all of this stuff is on GitHub. So this is the program, network.py, a module to implement the stochastic gradient descent learning algorithm for a feed-forward neural network. Gradients are calculated using backpropagation. Note that I have focused on making the code simple, easily readable, and easily modifiable. It is not optimized and omits many desirable features. Okay, so these are the standard imports. And now you have the NumPy class, sorry, the network class. So first of all, you have the initializer, the constructor. The list sizes contains the number of neurons in the respective layers. So this is, we have already discussed this. Then you have they have essentially combined everything into one. Now you have the feed forward part. This is a stochastic gradient descent part. This is the update mini batch part. And now this is the part which we haven't really discussed, which is back propagation. It returns a tuple nabla b and nabla w representing the gradient for the cost function. Nabla b and nabla w are layer by layer list of numpy arrays similar to self.biases and self.weights. And these are bound to be similar, right? Because they have been initialized using the self.biases and self.weights, the shapes of self.biases and self.weights. So you get the activations, and then okay, so I think we shouldn't really get into it if this is going to be discussed in the next chapter, but you can go ahead and get an idea of what he's trying to do. You can also pause the video and try to look at it, or rather just go to the blog itself. And then you have the evaluate. Evaluate uh, evaluates how many results are correct. It returns the number of test inputs for which the neural network outputs the correct result. Note that the neural network's output is assumed to be the index of whichever neuron in the final layer has the highest activation. And finally, you have the cost derivative. It returns the vector of partial derivatives. And yep. And apart from that, you have the sigmoid and the sigmoid prime. Sigmoid prime is just a derivative of the sigmoid. So if you try calculating the derivative of the sigmoid, you'll notice that you get something like this. Okay. How well does the program recognize handwritten digits? Well, let's start by loading in the MNIST data. I will do this using a little help of program mnistloader.py to be described below. We execute the following commands in the Python shell. Okay. Of course, this could be done in a separate Python program, but if you're following along, it's probably easiest to do in a Python shell. After loading the MNIST data, we will set up a network with 30 hidden neurons. We do this after importing the Python program listed above, which is named network. So 784 are the input neurons, 30 are the hidden layer neurons, and 10 are the output neurons, which correspond to the 10 different classes. Finally, we will use stochastic gradient descent to learn from the MNIST training data over 30 epochs with a mini batch size of 10 and a learning rate of eta equals 3. So now you're using the SDD function from the net uh, module which you have imported here, and you have inputted the parameters as discussed above. Note that if you are running the code as you read along, it will take some time to execute. For a typical machine as of 2015, it will likely take a few minutes to run. I suggest you set things running, continue to read, and periodically check the output from the code. If you're in a rush, you can speed things up by decreasing the number of epochs, by decreasing the number of hidden neurons, or by using only part of the training data. Note that production code would be much faster. These Python scripts are intended to help you understand how neural networks work, not to be high performance code. And of course, once we have trained a network, it can be run very quickly indeed on almost any computing program. For example, once we've learned a good set of weights and biases for a network, it can easily be ported to run in a JavaScript in a web browser or on a native app on a mobile device. In any case, here is a partial transcript of the output of one training run of the neural networks. The transcript shows the number of test images correctly recognized by the neural network after each epoch. As you can see, after just a single epoch, this has reached 9,129 out of 10,000, and the number continues to grow. This is a trained network gives us the classification rate of 95% at its peak, epoch 28. That's quite 95.42%. That's quite encouraging as a first attempt. I should warn you, however, that if you run the code when your results are not necessarily going to be quite the same as mine, since we'll be initializing our network using different random weights and biases to generate results in the chapter. Okay, so he's saying that do not expect these to be the same, but they'll be in the same neighborhood, kind of. And for this, he's taken the best of three runs. So let us rerun the above experiment, changing the number of hidden layers neurons to 100. As was the case earlier, if you're running the code as you read along, you should be warned that it takes quite a while to execute. On my machine, the experiment takes tens of seconds for each training epoch, so it's wise to continue reading in parallel while the code executes. Again, now the hidden layers are 100, similar stuff, and this improves the result to 96.59%. At least in this case, using more hidden neurons helps us to get better results. Okay, reader feedback indicates quite some variation in results for this experiment, and some training runs give results quite a bit worse. Using the techniques introduced in chapter 3 will greatly reduce the variation in performance across different training runs for our network. Okay, that is understandable because after all, everything is being initialized randomly. Of course, to obtain these accuracies, I had to make specific choices for the number of epochs, the mini batch, the learning rate. As I mentioned above, these are known as hyperparameters for our neural network. In order to distinguish them from the parameters which are weights and biases learned by our learning algorithm, if we choose our hyperparameters poorly, we can get bad results. Suppose, for example, if our learning rate was 0.001, you can see that you are getting very poor results. However, you can see that the performance of the network is getting slowly better over time. That suggests increasing the learning rate, say to 0.1, 0.01. If we do that, we get better results, which suggests increasing the learning rate again. If making a change improves things, try doing more. If we do that several times over, we'll end up with a learning rate of something like 1 and perhaps fine tune to 3, which is close to our earlier experiments. So even though we initially made a poor choice of hyperparameters, we at least got enough information to help us improve our choice of hyperparameters. In general, debugging a neural network can be challenging. This is especially true when the initial choice of hyperparameter produces results no better than random noise. Suppose we tried a successful 30 hidden neuron network architecture from earlier, but with the learning rate changed to 100. You'll see that in fact the learning rate is so high now that it is coming down. The number of correctly guessed uh, images are coming down. Now imagine that we were knowing coming to this problem for the first time. Of course, we know from our earlier experiments that the right thing to do is decrease the learning rate. But if we were coming to the problem for the first time, then there wouldn't be much in the output to guide us on what to do. We might worry not only about the learning rate but also about every other aspect of the neural network. We might wonder if we've initialized the weights and biases in a way that makes it hard for the network to learn. Or maybe we don't have enough training data to get meaningful learning. Perhaps we haven't run for enough epochs. Or maybe it's impossible for a neural network with this architecture to learn how to recognize handwritten digits. Maybe the learning rate is too low, or maybe the learning rate is too high. When you're coming to a problem for the first time, you're not always sure. And this is quite a good paragraph, I'd say. This summarizes how you'll feel for the first time when you're tackling any new problem. The lesson to take away from this is that debugging a neural network is not trivial, and just as for ordinary programming, there is an art to it. You need to learn the art of debugging in order to get good results from neural networks. More generally, we need to develop heuristics for choosing good hyperparameters and a good architecture. We will discuss all these at length through the book, including how I chose the hyperparameters above. Okay, finally, an exercise. Try creating a network with just two layers, an input and an output, no hidden layer. Try and the network using SGD. What classification accuracy can you achieve? So I'd leave this up to you because I have not set this up in the local environment, but you can try this out. So earlier I skipped out the detail of how the MNIST data is loaded. It's pretty straightforward. For completeness, here's the code. The data structures used to store MNIST are described in the documentation string. It's straightforward stuff, tuples and list of NumPy, ND, n-dimensional array objects. Think of them as vectors if you're not familiar with ND arrays. So a library to load MNIST and so on. Okay, so you can go ahead and read this code. I'm not going to focus on this part. I said above that a program gets pretty good results. What does that mean? Good compared to what? It's informative to have some simple non-neural network baseline to compare against, to understand what it means to perform well. The simplest baseline of all is to guess randomly. That will be right about 10% of the time. We are doing much better than that. What about a less trivial baseline? Let us try an extremely simple idea. We'll look at how dark an image is. For instance, an image of a 2 will typically be quite darker than a 1, just because more pixels are blackened out, as the following example illustrates. This suggests using the training data to compute average darkness for each digit. When presented with a new image, we compute how dark the image is, and then guess that it's whichever digit has the closest average darkness. This is a simple procedure and is easy to code up. So I won't explicitly write out a code. If you're interested, it's in the GitHub repository. Okay, but it's a big improvement over random guessing. Getting 2225 out of the 10,000 test images correct. That is a 22.25% accuracy. It is not difficult to get other ideas which achieve accuracies in the 20 to 50% range. If you work a bit harder, you get over the 50% range. But to get higher accuracies, it helps to use established machine learning algorithm. Let us try using one of the best known algorithms, the support vector machine or SVM. If you are not familiar with SVMs, do not worry. We are not going to need to understand the details of how SVMs work. Instead, we will use the Python library called scikit-learn, which provides a simple Python interface to a fast C-based library for SVMs known as libsvm. If we run scikit's SVM classify using the default settings, then it gets 9435 out of the 10,000 test images correct. That is a big improvement over a naive approach of classifying images on based on how dark it is. Indeed, it means that the SVM is performing roughly as well as our neural networks, just just a little worse. In later chapters, we will introduce new techniques that enable us to improve our neural networks so that they perform much better than SVM. Okay, that is not the end of the story. However, the 9435 of 10,000 results is for scikit-learn's default settings for SVMs. SVMs have a number of tunable parameters, and it's possible to search for parameters which improve this out-of-the-box performance. I won't explicitly do this search, but refer to this blog post by Andreas Muller if you would like to know more. Muller shows that there are some work optimizing shows that with some work optimizing the SVM parameters, it is possible to get the performance up to 98.5% accuracy. In other words, a well-tuned SVM can make an error on only about 1 in 70 digits. That is pretty good. Can neural networks do better? In fact, they can. At present, well-designed neural networks outperform every other technique for solving MNIST, including SVMs. The current 2013 record is classifying 9,979 out of 10,000 images correctly. This was done by Lee Van, Matthew Ziele, Sixin Zhang, Jan LeCun, and Rob Fergus. We'll see most of the techniques they used later in the book. At that level, the performance is quite close to human equivalent and it's arguably better, since quite a few of the MNIST images are difficult even for humans to recognize with confidence. For example, yep, these seem very arbitrary and ambiguous. I trust you'll agree that those are tough to classify. With images like these in the MNIST set, It's remarkable that neural networks can classify all but 21 of the 10,000 test images. Usually, when programming, we believe that solving a complicated problem like recognizing the image digits requires a sophisticated algorithm. But even the neural networks in the Vaughan et al. Paper just mentioned involve quite simple algorithms. Variations on the algorithm we have seen in this chapter. All the complexity is learned automatically from the training data. In some sense, the moral of both our results and those in more sophisticated papers is that for some problems, simple learning algorithm and good training data has a more or equivalent performance to a sophisticated algorithm alone. Okay, so now we are finally in the toward deep learning section. While our neural network gives serious performance, that performance is somewhat mysterious. The weights and biases were discovered automatically, and that means we don't immediately have an explanation of how the network does what it does. Can we find some way to understand the principles by which our network is classifying handwritten digits? And given such principles, can we do better? To put these questions more starkly, suppose that a few decades hence, neural networks lead to artificial intelligence. Will we understand how such intelligent networks work? Perhaps the network will be opaque to us, with weights and biases we don't understand, because they have been learned automatically. In early days of AI research, people hoped that the effort to build an AI would maybe help us understanding the principles behind intelligence and maybe the functioning of human brain. But perhaps the outcome will be that we end up understanding neither the brain nor how artificial intelligence works. To address these questions, let us think back to the interpretation of artificial neurons that I gave at the start of the chapter as a means of weighing evidence. Suppose we want to determine whether an image shows a human face or not. Okay, so these are the credits for the images. We could attack the problem the same way we attack handwriting recognition by using the pixels in the input image as input to a neural network with the output from the network a single neuron indicating yes, it's a face or no, it's not a face. Let us suppose we do this, but that we are not using a learning algorithm. Instead, we are going to try to design a network by hand choosing appropriate weights and biases. How might we go about it? For getting neural networks entirely for the movement, a heuristic we could use is to decompose the problem into subproblems. Does the image have an eye in the top left? Does it have an eye on the top right? Does it have a nose in the middle? Does it have a mouth in the middle? Uh, is the hair on top? And so on. If the answer to several of these questions are yes, or even just probably yes, then we will conclude that the image is likely to be a face. Conversely, if the answers to most of the questions are no, then we will conclude that the image probably is not a face. Of course, this is just a rough heuristic and it suffers from many deficiencies. Maybe the person is bald so they have no hair. Maybe we can only see part of the face or the face is at an angle. So some of the facial features are obscured. Since the heuristic suggests that if we can solve the sub-problems using neural networks, then perhaps we can build a neural network for face detection by combining the networks for the sub-problems. Okay, so here's a possible architecture with rectangles denoting the subnetworks. Note that this isn't intended as a realistic approach to solving the face detection problem. Rather, it is to help us build an intuition for how neural networks work. So, some hidden layer might be looking for eye in the top left, some might be looking for a nose, and so on. It is also plausible that the subnetworks can be decomposed. Suppose we are considering if there is an eye in the top left, this can be decomposed. Is there an eyebrow? Are there eyelashes? Is there an iris? And so on. Of course, these questions should really include positional information as well. Is the eyebrow in the top left and above the iris? That kind of thing. But let us keep it simple. The network to answer the question, is there an eyeball on the top left, can now be decomposed into these three questions. Those questions can too be broken down further and further through multiple layers. Ultimately, we will be working with subnetworks that answer questions so simple that they can easily be answered at the level of a single pixel. Those questions might, for example, be about the presence or absence of very simple shapes at particular points in the images. Such questions can be answered by single neurons connected to raw pixels in the image. So I think this is incredibly well written, and I couldn't have done any better job at explaining this myself. The end result is a network which breaks down a very complicated question, does this image show a face or not, into a very simple questions answerable at the level of single pixels. It does this through a series of many layers, with each layer answering very simple and specific questions about the input image, and later layers building up a hierarchy of even more complex and abstract concepts. Networks with this kind of many layer structure, two or more hidden layers, are called deep neural networks. Of course, I haven't said how to do this recursive decomposition to subnetworks. It certainly isn't practical to hand design the weights and biases. Instead, we would like to use learning algorithms so that a network can automatically learn the weights and biases, and thus the hierarchy of concepts from training data. Researchers in the 80s and 90s tried using stochastic gradient descent and back propagation to train deep networks. Unfortunately, except for a few special architectures, they did not have much luck. The networks would learn, but very slowly and in practice, often too slowly to be useful. Since 2006, a set of techniques has been developed that enable learning in deep neural nets. These deep learning techniques are based on stochastic gradient descent and backpropagation, but also introduce new ideas. These techniques have enabled much deeper and larger networks to be trained. People now routinely train networks with 5 to 10 hidden layers, and it turns out that these networks perform far better on many problems than shallow neural networks, that is, networks with just a single hidden layer. The reason, of course, is the ability of deep nets to build up a complex hierarchy of concepts. It is a bit like the conventional programming languages use modular design and ideas about abstraction to enable the creation of complex computer programs. Comparing a deep network to a shallow program is a bit like comparing a programming language with the ability to make function calls to a stripped down language with no ability to make such calls. Abstraction takes a different form in neural networks than it does in conventional programming, but it is just as important. So this was a great introductory blog. Took us quite a lot of time, but I believe that it was really worth it. Now, hopefully, we'll start with the how the back propagation works, algorithm works, and I hope that you like this video. And always, you can go and support the creator of these blogs. You can donate and donate in all of these various ways. So, thank you, and I'll catch you guys in the next video.